Today we discuss about convergence theorem or convergence theory. First we discuss some definition of convergence, and then we also further proceed. Okay. We also known in previous class also pointwise convergent and uniform convergence. Okay. Now we discuss convergence theorem. So we write this one and definition way. We first write this definition of convergence. Definition is that let X norm be an inner product space. Be an inner product space. Okay, be an inner product space, and X in one sequence, X in subset of X, such that inner product of X and Y equal to 0 for all Y belongs to X. If X n tending to X for X belongs to X, then xy equal to 0. Now this one we write not in definition, we write this one is theorem. Okay, the statement of this theorem, I think. So what we prove this, we known about that x n tending to X. Okay, for X belongs to X, then this implies that xy equal to limit n tending to infinity x n y equal to limit n tending to infinity x n y of inner product. Then what we do? We do this one is given, this one equal to 0. So what we get? We get xy equal to 0. Just to prove easy proof, but we discuss about that here. Okay, just we write in this way and we discuss about this. Let X norm be a inner product space and X in some sequence subset of X, then such that X and Y of inner product equal to 0 for Y belongs to X gives for X belongs to X, xy inner product equal to 0. Now we also obviously erase this portion and going to further discussion about that. One important proposition we handle now. We write the statement of this proposition first. Yeah, proposition. Okay. Let x and y and be Cauchy sequences. Let x and y and be Cauchy sequences. Let x and y and be Cauchy sequences in an inner product space. In an inner product space, let x and y and be a Cauchy sequences in an inner product space. Inner product space and inner product space X. Define a sequence Zn. Define a sequence written in ky zn equal to x n y n of inner product for all n belongs to n, then zn be Cauchy. Then zn be Cauchy, and it is convergent. And it is convergent also. Okay, so what we do, we now prove of this. So zn because we have to prove, then zn obviously convergent. Just xn and yn are Cauchy sequences. Okay, so what we done now, uses of x and y and Cauchy sequences. We also show that zn be Cauchy. Okay, so we start about first we start about xn and yn be Cauchy. Okay, then here write for mn belongs to n, mod of zm minus zn equal to xm ym minus xn yn. This equal to xm ym minus xm yn plus xm yn minus xn yn. Okay, this less than equal to xm yn minus xm yn plus xm yn minus xn yn. This equal to xm yn ym minus n. This equal to xm minus xn yn. Okay, this less than equal to norm of xm, norm of ym minus yn. Here norm of xm minus norm of xn, norm of yn. Okay, now obviously xn and yn be Cauchy, so we is our portion. And what we do here less than norm of xm multiplied by k1, and here norm of xm minus xn multiplied by k2 for some k1 and k2 greater than 0. Okay, here obviously here we write not here ym minus yn. Okay, multiplied by, since xm and yn are Cauchy, so they are bounded. Okay, xm and yn be Cauchy, so they are bounded. we write here for some k1 k2 greater than 0, and and since x and y and v cosy, so bounded, then norm of x m less than equal to k and norm of y m less than equal to k2 for all m greater than equal to p or p belongs to. Okay, now then what we get? We get here again n m tending to infinity, then we get zm minus zn tends to 0 as xm minus xn tends to 0 and ym minus yn tends to 0. Because those are cosy, so this one is happen. Okay, now we're going to further discussion about that. This implies that Zn be cosy since k is complete, since k be complete. So complete means every Cauchy sequence obviously convergent, then Zn be convergent. Okay, so we also prove this. Now we prove two theorem, another one theorem and one proposition. First one is just x and y inner product equal to 0 and x n tending to x, then xy inner product equal to 0. And next one is x and y and Cauchy sequences in an inner product space x and Zn in K defined by Zn equal to inner product of x and yn. Then Zn is Cauchy and it is convergent also. Okay, now we write this weak convergent definition. Okay, weak convergent definition. Weak convergence definition. Let xn be a sequence in an inner product space. Let xn be a sequence in an inner product space x norm and x belongs to x and x belongs to x. Then what we do? We do that first one. We say xn converges to xn converges to x, that is, whereas our portion, that is xn converges to strongly, that is xn strongly converges to x. This if norm of x and difference x tends to 0 as n tending to infinity. Okay, again we give second definition. Now we say xn weakly converges to x if x and difference x y equal to 0 tends to 0 as n tending to infinity, and for all y belongs y subset or all y belongs to x. Okay, then now we erase all this portion and going to perform proof of some proposition. Okay, proposition. Let xn be a sequence. Let xn be a sequence in an inner product space x norm. In an inner product space. In an inner product space x norm such that xn tending to such that xn tending to x such that xn tending to x for some x belongs to for some x belongs to x, then x weakly converges to x. Okay, now we have to prove of that. So what we get x and difference x y tends to 0. Okay, this implies for arbitrary y belongs to x, then x weakly converges to x. Next proposition. Next we write this statement of this proposition. That means first we prove strong convergence implies weak convergence in an inner product space. Now we obviously now contradiction is not hold, but if we added some condition, then weak convergence implies strong convergence. Which condition we added, we now discuss about that. So we write now here xn be a sequence in an inner product space. in an inner product space X norm such that X in weakly converges for some X belongs to X, and norm of X in converges to norm X, then X in converges to X. Okay, so we now prove this proportion. How we prove it? We write this. Note that norm of xn minus x square equal to xn difference xn difference x equal to norm of xn square difference xn x difference xn slash norm of x square equal to norm of xn square norm of x square. Okay, difference 2 of real x and x. This one marked as 1. Next we discuss about that. Then given that, which one given that given that this one x in weakly converges. This implies that x in difference x y tends to 0 as y belongs to x. Okay, now this implies what? This implies x in, if we put here x in difference x, because tends to 0, here x belongs to x, put y equal to x, then what we get? Then we get, also is our portion, then we get x in x tends to x equal to norm x square. Okay, and obviously norm of x in tends to norm x, this one also given. So what we find that hence from 1 we get norm of x in difference x whole square tends to 0 as intending to infinity. Okay, so what we get? We get this conclusion part, norm of x in difference x tends to 0 as intending to infinity, x in converges to x. Okay, now we also discuss about some example about weak convergence and strong convergence. Some example we also create this example. Let x equal to L2 with p norm, I think that means with L2 norm. Then xy is defined this inner product equal to n equal to 1 to infinity xn yn for all xy belongs to L2. Let En be a sequence in L2. Let En be a sequence in L2. Then E1 equal to 1 0 dot 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 En equal to this one equal to En minus En equal to root 2. Hence En minus En norm does not tends to 0. Hence it is not Cauchy. Hence it is not Cauchy. Okay. Now hence En is not strongly convergent. So we also construct some En in L2. This one also not strongly convergent. Okay. Then what we see? We see UN is weakly convergent or not. Next we shows that here E1 equal to this one, E2 equal to En equal to then En converges to X. Belongs to this L2. Now note that En y less than equal to norm of En difference X norm of y. This equal to norm of En norm of y. This equal to norm of y. Okay. Now let y belongs to let y belongs to L2, then en a difference x y equal to en y. Okay, equal to yn tends to 0 as n tending to infinity. Hence what we get? We get en difference x y tends to 0 as n tending to infinity for all y belongs to L. So En weak converges to this one. Now we discuss orthogonal set and orthonormal set. We also see one example of En of sequences which are not strongly convergent but weakly convergent in L2. Now we discuss about one orthogonal set and orthonormal set definition. Okay, orthogonal set. Orthogonal set. Let S be a set in an inner product space. Let S be a set in an inner product space. X naught. Then S is said to be. Then S is said to be orthogonal if equal to 0 for all xy belongs to S with x not equal to y. Let S be a set in an inner product space x naught. Then S is said to be orthogonal if first xy equal to 0 for all xy belongs to S with x not equal to y, and number 2 norm of x equal to 1. Okay, now we stop here and obviously going to further discussion about in next class.